Okay, Matter 1 has a larger work function compared to Matter 2. Both are illuminated with the same short wavelength ultraviolet light. Do photoelectrons from Matter 1 have a higher speed, a lower speed, or the same speed as photoelectrons from Matter 2? Explain. Okay, good. So this one is talking about different work function and versus the speed of the photoelectrons ejected. So this is about work function versus we can say Vmax. So this is between what? Between work function versus the maximum speed of photoelectron ejected. As well, you can say work function is like the binding energy, binding energy of the metal surface. So if higher work function means it bind the electron with higher binding energy, so it's harder for the electron to escape. If lower work function means the photoelectron easy to escape. Understand? So both have this illuminated with the same ultraviolet light. You see, same ultraviolet light, UV light lah. UV light, same wavelength, same wavelength. So they receive same photon. They receive the energy of photon, energy of incident photon. This is called the incident photon, is constant or the same for both. Understand? HF, not H lambda. HF, HF, or I can say this one is right somewhere. Yeah, HF. I just want to put it over here. This HF is also HC over lambda. Okay. So they are the same. They use the same incident photon, so they receive same amount of energy. What I can say, it receives same amount of energy. So what is the equation again? Back to our main equation. To explain this, we go back to our main equation, which is this equation. Einstein photoelectric equation. Einstein photoelectric equation. Just remember this. Yeah, this is the core part in this chapter. E equal to Kmax plus work function. Yeah, just write back this equation. E equal to Kmax plus work function. E equal to Kmax plus work function. So, okay. So what I can say is the constant one is this one. Yeah. This is considered to be constant. Constant because they say they receive same amount of incident photon. So they receive same amount of energy. However, this K, the work function is different. Different metal surface, isn't it? Different metal surface. So okay, how to write it? Okay, since we have two conditions, one is Matter 1 and one is Matter 2, so better we write it out in two columns. Okay, so this one is Matter 1. Okay, Matter 1. Wait a second. This one use Matter. This one use Matter 1. This one use Matter 1, and this one use Matter 2. Yeah, use Matter 2. So this one use work function 1, and this one work function 2. Understand? Work function 2. So energy of photon is same wavelength, means constant. The E is constant. The energy is constant. Okay. The energy of incident photon. The energy of incident photon is constant for both. It's the same for both. What differ is just the Vmax, Vmax, Kmax lah. So they have this different Kmax. This one Kmax 1, this one Kmax 2. Okay. So what I can say is this one, the equation become E equal to K max plus work function. This one is K max 1, work function 1, and then same goes to that one. E equal to K max plus work function. This one should be work function 2, K max 2. Okay, and then we can further derive it. K max, you get half. K max is half mv square, and also EVS, stopping potential, is over here. So I can write it like this. I can also write it like this. Okay. Let us just write it out. Everything. Let us just write everything out. Yeah. HF equal to half mv max plus square plus HF naught. This one is HC over lambda naught. Do I need to write everything actually? Okay, I think I just I think I just same wavelength, yeah, same wavelength. Okay, I might just write down everything. HC over lambda equal to EVS. That one can change to EVS, and then this one is HC over lambda naught. Okay, this one is considered to be Vmax 1. This one is F naught 1. Yeah, this one is stopping potential also different. This one also different. Okay. Wait. Let me copy first to the other side. Copy first to the other side. Okay, and then only a label. This one all 1, 1, 1, 1. Yeah. This one have 2, 2, 2, 2. All the rest, this one is about this part. This part is constant. All this part is constant. Constant. Yeah, constant. Yeah. Because he say this part is constant because he used the UV incident photon, isn't it? Which is the violet light. Both of them use the same incident photon. Okay, use the same incident photon. Because ultraviolet light. Ultraviolet is not violet actually. Yeah, it's not violet. It's ultraviolet. It's not actually violet color. Yeah, ultraviolet has no color. Yeah, actually ultraviolet has no color. You cannot see the ultraviolet light also. Yeah, ultraviolet. Okay, so they all this side have the same value. Yeah, because it is constant, isn't it? Because the energy of incident photon is constant. Energy of incident photon is constant. So they receive the same ultraviolet light, so they have the same energy. Yeah, same energy of incident photon, same frequency of incident photon, same wavelength. Same wavelength of incident photon. Same energy, same frequency, and same wavelength of incident photon. Okay, what different is just between Kmax and work function. So they have different Kmax, different work function, different Vmax, different stopping potential, different threshold frequency, different threshold wavelength. Understand? Okay, so now you ask me, yeah, based on this equation, you ask me, the method 1 has a larger work function than method 2. So what I can say is, from here I can see, okay, put it over here. So he's saying that the work function for method 1, is larger than method 2. Is larger than work function for method 2. Work function larger than work function for method 2. So that means work function for method 1 is bigger work function for method 2 is smaller. So what it means is, okay, let me write it down. Yeah. So what it means is, the work function of method 1 is bigger. Work function of method 1 is bigger. That means the Kmax should be smaller. Kmax should be smaller. Threshold frequency of method 1 is higher. The Vmax is smaller. Yeah, the threshold frequency, this one threshold wavelength. With threshold frequency is higher, that means the threshold wavelength is smaller lah. Smaller. Stopping potential. Okay, this one. Vmax is lower, so stopping potential also lower. Yeah, stopping potential also low. Actually, this whole thing is when the threshold wavelength become smaller, that means this whole thing is become bigger. Understand? Because it divide by a smaller value, become bigger. So how about method 2? Method 2 has a low work function. Yeah, method 2 has a low work function. Okay, I just want to write this one go up, this one go down, right? So method 2 has a lower work function. Method 2 has a lower work function. It has a lower work function, lower threshold frequency, a higher threshold wavelength. That means this one is lower lah. Okay. Lower work function, that means it has higher Kmax, higher Vmax, and higher stopping potential. You understand? So what I can say is this one. Okay, just want to write it over here. So what I can say is, if I want to compare, okay, work function for method 1 is higher than work function for method 2. That means the Kmax for method 1 is lower than Kmax for method 2. Kmax for method 1 is lower than Kmax for method 2. Or we can say the Vmax for method 1 is lower than Vmax for method 2, and the stopping potential also lower. Stopping potential method 1, stopping potential for method 1 and lower than stopping potential for photoelectron ejected from method 2. Do you understand the reasoning behind this? Do you understand the reasoning behind this? Okay, you just want to make a bracket there, yeah, so that you can see it clearly. Okay. So what I can say is, this method 1 has a higher binding energy. Method 1 has a higher binding energy. Okay, higher binding energy. So the photoelectron ejected is has less kinetic energy, because the electron has to the energy they receive, energy of the energy that received by the electron is the same for both metal, because they receive the same ultraviolet light energy, same amount of energy for both. Yeah, and same energy received by both electron. However, for metal 1, most of the energy received is used to overcome the very high binding energy, very high work function. So it left with very small amount of kinetic energy. Yeah, so that means the kinetic energy ejected is very small. So the maximum speed also become small. The speed ejected also becomes small. So you need a very low stopping potential to stop the very slow photoelectron. Understand? You need a very low stopping potential to stop the very slow photoelectron. However, for method 2, because it has very low work function, that means most of the energy received, very little amount of energy received is used to overcome the work function, because the work function is for method 2 is very low. Okay, so there's a lot of remaining energy as the kinetic energy. There's a lot of remaining energy as the kinetic energy. So the kinetic energy of the electron ejected is very high. So when very high kinetic energy, it has high maximum speed, and you also need a very high very high stopping potential to stop the photoelectron. Understand? It's just like this example I have taught you before, okay, in the lecture video, like this. This teeth is just like the photoelectron, okay. This is like metal 1. You see that? This is like metal 1. This is like metal 2. Metal 1 has very high work function. It's like have very high wall. So this photoelectron, this teeth is like photoelectron. They have a lot of energy, but these teeth need to use a lot of energy to jump over the wall. Yeah, you jump over the wall. So it use up a lot of energy to jump over the very high wall. So after he jumped the wall, he become very tired. So has very low kinetic energy. Understand? Has very low kinetic energy, and after that it has very low speed. Okay, compared to this one has a low work function. Low work function, that means this teeth can easily jump over, and it still have a lot of kinetic energy remaining. And it has very high speed. You understand? So okay. So back to this one. Metal 1 has very high work function than metal 2. That means metal 1 has a lot of has very high binding energy. So okay, metal 2 has a very low work function. So that means the photoelectron use up. Okay, metal 2 has very low work function. That means the electron use up very less energy to overcome to eject from the electron. So it's still left with very high kinetic energy. Metal 1, the metal surface has very high binding energy. So the electron have to use up a lot of energy to overcome the work function. So when ejected, because it already used up a lot of energy to overcome the work function, all right. Because the electron has used up a lot of energy to overcome the work function, so it left with very few amount of kinetic energy. So so the photoelectron ejected has very low kinetic energy, so it has very low speed. Low speed compared to photoelectron ejected from metal 2. Photoelectron ejected from metal 2, because the metal 2 has very low binding energy, very low work function. So the electron just use up a little amount of energy to overcome the work function to release from the metal. So since you just use up a little amount of energy to overcome the work function, so it still have a lot of remaining kinetic energy. Once it ejected from the metal surface. So since it has very high kinetic energy, that means it still have very high speed. And then you need a high stopping potential to stop it. For metal 1, it has low kinetic energy, so it has very low speed. So you need a low stopping. You just need a very small stopping potential to stop the photoelectron. Okay. So that's the conclusion for this question. So I hope you understand. And okay, that's all for these questions. Okay. So just now back to this question: do photoelectron from metal 1 have higher speed, lower speed, or same speed as the photoelectron for metal 2? I can say metal 1 has very high work function. So the photoelectron has used up a lot of energy. Okay, maybe I should write something over here. So this is the conclusion. Yeah. So metal 1 has very high work function. Yeah. So photoelectron has used up a lot of energy to overcome the work function to eject from metal 1. So thus left with very low kinetic energy and low speed. Okay. So the rest, why I write so many things over here, I not just want to compare between work function versus the speed. I also want to relate other things, like how about the threshold frequency, how about the threshold wavelength, what will happen, and how about the stopping potential. So that is other thing you can get from this equation. You see, so many things can get from the equation about the threshold wavelength, threshold frequency, work function, Vmax, Kmax, stopping potential. These are the thing you just work around with the equation and you can get so many other things, right? So I already explained in this in my lecture video. Okay, I see I do comparison between work function and threshold frequency, yeah, and the stopping potential, Kmax, and work function also by just using the photoelectric Einstein photoelectric equation. Okay, so that's it for this question. Bye.